Good morning, dear students. Welcome to another session of DSP Architecture and Algorithms. So in this part, we'll be starting off with the programming aspects, memory interfaces and I/O interfaces. So these all aspects we'll be discussing in this part of the sessions. So let us start off with few things, that is applications of programmable DSP devices. Since we had gone through what are the different features which are present with the DSP devices, such as for shifting, how it can be done in one machine cycle, then how can multiplication be achieved in one machine cycle, or then apart from that, we discussed how on-chip memory and off-chip memory play a vital role in speeding up the executions. So all these things we had discussed: parallelism, pipelining. So these are all features of DSP devices, which makes it slightly different from your regular microcontroller devices or microprocessor devices. So now, when we seek for DSP devices, right, it finds its application in number of things. Say, let it be from a small aspect to a very large aspect. Say, if you want to, for example, if you identify applications, say, related to your recent advancements in AI, that is artificial intelligence. So there also the processing, if it is required in real time, then you go ahead with the DSP devices. For example, you want to identify whether a object is present or not in front of a vehicle, so which can be used for autonomous controls of the vehicle. So in those cases, the application should run in real time, so there the speed requirements are very high. So in such cases, what we can do is we can go for DSP devices which provides these all aspects. I cannot go for your regular microcontroller because it will consume lot of time. So this may be problematic when we deal with the real time systems which require fast execution and obtaining very quick results. So example I took of AI. If you just speak of general aspects also, there also you can deal with the DSP devices. For example, if you go for image processing, in image processing also you can deal with the DSP devices, wherein you can perform some transformations on the images, and then use those coefficients for some other purposes to identify, say, some parameters in that image, then go ahead with some decisions. So all those things can be done. So image processing. Then if you speak from other point of view, say a speech recognition, then in simple form, signal processing also can be achieved. Speech processing is nothing but again a part of a signal processing itself, because it will be processing the signal related to your voice. So these are just a few things to name around wherein DSP devices finds its applications. So let us see a few of the applications oriented to DSP devices over here. So previously we had seen that what does a DSP system consists of. So I'll just be going through quickly through this one. So DSP system will be consisting of an anti-aliasing filter to overcome the aliasing effect, which can be introduced due to the sampling. So if your Nyquist criterion is not satisfied, then aliasing effect will be observed. So in order to why this might happen is, another thing is, in the analog signal you might encounter few signals which are at higher frequency range, which is not intended. Say in a voice, this thing, say the range you want is 20 hertz to 20 kilohertz. So due to some spikes or noise present in that signal, you might get more than 20 kilohertz. So if you want to remove those, so pass it through a low pass filter which passes only as a 20 hertz to 20 kilohertz. So which will be acting as an anti-aliasing filter. Then once you filter the signal, so what you're doing is you're trying to achieve the Nyquist criterion based on the sampling circuit what you have designed. So then we have sample and hold circuit. What it does is it takes the analog signal, converts this thing into discrete signals. So once the samples are obtained, it is passed through A to D converter. So these pulses are passed through actually quantizer. So sampling and quantization together actually forms your A to D converter. So after the samples are obtained, it is passed through a quantizer, and after quantizer, you will be getting a digital signal at this point. Now, if you want to process the signal in digital this thing, you can go for DSP processor. So once you process the signal, you'll be getting, say, you perform, say, DCT on this signal. You perform DCT on this signal, and you'll be getting the result at this point. at the other point. So this is also in digital in nature, and this input to the DSP processor is digital and output is also digital. Now, if I want to see the signal again on, say, the process signal on the oscilloscope, just for example, then what happens is directly I cannot give the digital signal. What I have to do is I have to convert that signal back into analog form, pass it through the filter to remove any distortions which are present, and then I'll be getting the overall analog signal. So this is what your DSP system will be consisting of. Now coming down to DSP-based biometry biotelemetry receiver. So what is biotelemetry receiver? It is say a biological instrument which say transmits biological signals and tries to analyze those things. So biological signals, for example, you might have seen the ultrasound scan. So in that, the baby's health and other heart rate, everything is monitored with the help of the devices without actually having any invasive techniques. So you're trying to send in ultrasound signals and try to receive it back, and that kind of receiver we term it as biotelemetry receiver. So these signals, like you transmit and you try to receive it back. So you are transmitting it at distance places, or the distance may be small enough also. So you are transmitting these biomedical signals and trying to see what is happening or what is the data which is present in that signal. So it is basically relates to physiological information, which is nothing but the biologic, which is related to the biological aspects. So here these informations are transmitted over a long range, that is remote location. So this is how biotelemetry receiver is implied. Now this is how the receiver will look like. So before the receiver, the data, whatever is acquired, say you are trying to identify the heart rate of the baby in the womb, in the mother's womb. So you monitor it with the ultrasound and ECG signal, everything you try to analyze. So that information is captured. Say it will be in analog form first. Information captured is in analog form. Then what you do is, if you want, you can convert it into digital form, pass it through a DSP processor, and then before transmitting it, what you can do is you can pass that signal through an encoder. You pass that signal to an encoder, and then you modulate the signal and transmit it over a long distance. So basically, whatever signal you are getting, signal you are getting, you are modulating that signal. So intermediate, again, n number of processes are there that we are not presenting over here. So whatever signal we are getting, that is the signals related to the biological aspects we are modulating that signal. We are modulating that signal, and then we are transmitting it. We are transmitting this signal. So this transmitted signal is received by the biotelemetry receiver. Since this information, we are assuming that it is related to biotelemetry information. That is physiological information of the signals which are related to biological aspects. So now what has to be done is it has to do the reverse process of whatever is present over here. So whenever the signal is received, it should be demodulated first. And then if processing has to be done, analog processing, since the result here will be analog, you can pass it through a analog processing this thing. And then when you get, if you get a digital signal over here, you can perform the digital signal processing aspect over here. Now I want to read what is the information which is present present in this part. That is whatever signal we had received. I want to know what is the information. Say for example, here it is like ECG and the heart rate, what they are specifying. ECG and the heart rate. So that information is received from the receiver transmitter end. It is modulated and then it is transmitted. So that information comes in over here. You demodulate it. You process the signal. Say if you want to remove some distortions, you can go ahead with removing that distortions. Then give it to the digital signal processing, wherein that information can be processed in its digital form. So if this information is in digital form, if we just see ECG signal or HR signal, it will be in analog form. So we should have a digital information which tries to obtain the digital to analog conversion of this and provide the ECG and HR information. So this is how a biotelemetry receiver system will be operating. So this is regarding the biotelemetry receiver. So demodulate the signal, it will be in analog form, do the processing of the signal. So the transmitted signal, you just remember that it will be still in analog form, because you'll be performing modulation of the carrier signal, which is in continuous form, no matter whether it is digital over here. So you'll be using digital modulation techniques and you'll be transmitting that. So you'll be getting that information in analog form. So once you get these are the steps what you can follow in order to read the information. So this is related to ECG and heart rate signals which are being transmitted from the remote end and which is being received at the receiver end. So now here, one important aspect what we have to check out is, suppose I have the ECG signal, I want to transmit it. So before transmitting, we can do one additional this thing which is called as encoding. Which is called as encoding. So in ITC, you might have studied why encoding has to be done and what is the purpose, how it helps in its transmission and other aspects. So encoding has to be done. So in this case, right, we can do encoding using one technique specified as pulse position modulation. So this is including both pulse position modulation, and it is also can be used for the pulse encoding. So here, what happens is, what is meant by pulse position modulation is, now in your simple terms, say for example, I have a signal, say this is 1 volt. So this is 1 volt, and there is a pulse of some width. So this is the pulse. So in a given time period, right? In a given time period, the position of the pulse decides what is this amplitude. That is, you are modulating the position of this pulse. You are modulating the position of this pulse and nothing else you are altering. So the characteristics, what is modified related to this pulse is its position. Its position. So in this case, what happens is, as for example, if it is 1 volt, say let us assume that this part, it is 1 volt. So it might be shifted to this position in a given time interval. Now, if it is 2 volt here, it might be shifted still further. If it is say 5 volt, it might be shifted towards the end. So 0 to 5 volt is the range what you're trying to go ahead. So in this case, you have pulse position modulation. So position defines what is its amplitude value. So it is like you're encoding this information in this pulse position modulation. At the same time, what you're doing, you are modulating the signal also. So in this case, we were discussing regarding two signals, right? So here during T1, it is say example ECG signal, and during T2, it is the heart rate signal, and T3 is one additional parameter which is put forth over there for, let's say, synchronization purpose. That is, sync pulses are present. So here we have total three pulses. That is, T3 is present for the compensation part. It is present for compensation part. So here we require sync pulses, because at the receiving end, if I lose the track of one of the pulse and if I move to some other, then rest of the information again I'll be losing. Suppose here I have the sync pulse. So if the receiver mismatches and starts off here, then what happens is two sync pulses are required. So this pulse might be identified as a sync pulse. So, but it is related to what? It is related to say ECG signal. So we'll be losing that information. So in order to avoid such kind of aspects, we go in for having sync pulses. So sync pulses are present, and in this case, we have total three time units which are specified. That is T1, T2, and T3. So here T1 is for, say for example, the ECG signal. T2 is for the heart rate, and T3 is the compensation interval which is present. So from here to here, we can see. Sorry, not from here. We can see that from this point to this point. That is the three. The sum of these three plus the 5 TP signals what we have. So this all gives rise to your sampling interval. So in this case, it is around 4000. So this is what is specified for pulse position modulation. Now, how do I decode this? So this is encoded information. And pulse position also gives some other information like identifying what is the peak value of the given signal. So those all things it helps us to identify. Now, how do I go ahead with the decoding of this PPM signal, that is pulse position modulated signal? So we have the pulses which are present, pulses which are present. Now, what this does is when the DSP receiver receives this signal, say it performs all the operation, it gets back this signal which we had. So this is the signal what we'll be transmitting. And when we receive it at the receiver, first we look out for the sync pulses. So after these two sync pulses, the first T1 is actually related to the ECG signal. So we try to identify at what interval the pulse is present. So that DSP timer notes down. So once this DSP timer notes down that at this timing interval, this pulse position is there. So based on that timing, it will try to estimate that it is, say, the voltage of the signal is around this, around say 1 volt, 2 volt, 3 volt. So depending on that. So after this signal is received, then it goes for the next time interval, that is T2. It sees where the pulse is present. That's at what time interval. So based on that, again, it decodes this information. So in this way, it will continue and it will be accessing all the information. So this is how decoding happens using the PPM signal. This is the decoding aspect of your biotelemetry receiver. So this is how it happens. So here we have the DSP system, which is related to the biotelemetry receiver implementation. So we at the receiver end, we get the PPM input. Then a PPM signal interface is provided. What it tries to identify, it tries to identify the timer with respect to say T1, T2. It tries to identify that. So based on that, interrupts are generated. So here, when timer, if I check from this point to this point, I got a pulse. So when I get this pulse, I send a interrupt to the DSP. I send the interrupt request. So when I receive that interrupt request, we have to process some aspects. So that processing will be done. And if you want to present the result of this interrupt over for example, if the first this thing is ECG signal, if it is related to ECG signal, so I get a pulse at this point. So interrupt will be generated. It will get to know that this interrupt is actually related to the processing of the ECG signal, this thing. So it will try to analyze what is that ECG signal value. And if I want to present it to the outside world, then I can pass it through the D2 DAC converter. And since here, because we are dealing with the two, this thing, ECG and HR, this thing, we have a dual DAC over here because we might be extracting two informations over there. That is one in T1 and one in T2. So this is how the DSP at biotelemetry receiver looks like. Okay. So this one thing system. So we have speech processing system. You might have come across many things now recently that you might be hearing that natural language processing and other stuff. So how these things are happening? So these things are happening based on the speech processing system what are present. So these speech processing systems also can utilize the DSP processors because it requires heavy computations over there. So if say your system wants to identify what is the speech you have, what are the wordings you have put forth, say for example, Alexa and other stuffs, they try to identify what you're speaking. So it is trying to process the speech, Amazon Echo, Alexa, so these things. So they're trying to determine what you're speaking. So you have seen in ads also that these things they are showing up. So how does it go ahead with these all things? How does it identify the speeches? So it basically tries to identify what is the pitch period, or it might use the pitch period information or any other technique in order to identify what is the wordings. It might make use of the artificial intelligence in order to club whether the sentence is formed properly or not. So it tries to identify it in that form and tries to give back the result. Say if I ask Google for say through Amazon Echo, if I ask for some DSP devices, so it will try to analyze that, it will put forth, and it will try to get back the information. Even in your mobile phones, you might have seen that Google this thing, when you start off speech this thing, it will tell, instead of typing, you can just speak out and try to see whether you get the search results. So even that is possible in these cases. So here, so this is how it goes around. So before going into that, you should know how the vocal cord actually works around, or what are the things which are present over here. So when we consider the human vocal system, right, at one end you have the closure which is related to the lips. That is, there is a termination with respect to the lips, and at the other end there is a termination due to the vocal cords. So this entire vocal tract is responsible for the speech generation, and along with the other things, that is velum, then the lips, tongue. So these all things help in generating the voices. Now, what does velum do is, velum, either it gets connected or disconnected, and based on this, the vocal tract will be changing its aspect, and it will be generating different sounds. And sometimes you might breathe faster in order to intentionally say you exhale the air. So at that time, you can see that different sounds are also made apart from what you're speaking. So these are just this is the say human vocal which is vocal system which is present. So at one end it is terminated with the vocal cords, at the other end it is terminated with the lips. Then lips, then tongue, then this vocal tract and vocal cords, velum, all together help in generation of the speech. The velum either gets connected or disconnected. Based on this, this vocal tract operates. So this is how the voice is being generated. Now, how do we go ahead with the production of this one? So here we can see that there is a block diagram which is related to the clipping autocorrelation pitch detector. So what is happening over here is, now whatever you are speaking uh, through your vocal cord, right, through your vocal system, it is having certain pitches associated with it within some given time period. So your main aspect is to identify this pitch in order to identify what are the words which we are speaking. Then apart from this, your system should also be able to identify whether it is actually the speech which is there, or it is something else. That is, whether it is a noise which is present. So these all things it should be able to identify. So you have to be able to estimate these pitches from your speech signal. So that is what you're trying to obtain. So how do I obtain the pitch information? I go in for what is called as autocorrelation. So autocorrelation is correlation of the signal with itself. Correlation of the signal with itself. So how do I obtain the autocorrelation? I make use of this aspect. That is here. If there are three levels of center clippers, that is for y of n, what we have assumed. This part, the product of this one gives you the autocorrelation information. That is, this gives you the entire autocorrelation information. X of n convolved with x of n. So this will give you the autocorrelation information. So that is what you're observing over here. So here we'll just go through this part. So what we have is the speech signal, which is in analog form. It is passed through a low pass filter, which will be obtained in the range of 0 to 900 hertz. So once this is done, it is passed through an analog to digital converter. So this is clipping autocorrelation pitch detector. It is trying to detect what is the pitch of this signal, what we are speaking. So when the signal is received, voice signal is received, it is first passed through a low pass filter, and this gives the signal in the range of 0 to 900 hertz. So once we obtain this, it is passed through the analog to digital converter, which will be giving you the digital signals of this speech equivalent. Now, after that, what is done is you divide it into sections of 30 milliseconds. So 30 milliseconds sections implies that there are total of 300 samples. Why 300 samples is the sampling rate. The sampling rate for the signal is considered to be 10K. 10 kilohertz. So if it is 10 kilohertz, then what is the timing interval? It is 0.1 millisecond. So one sample is of 1 millisecond, or one section is of 1 millisecond. So if I multiply it with 300, right? If I multiply this with 300, I'll be getting around 30. So 30 milliseconds I'll be getting around. So this is because of the 10 kilohertz sampling rate what is present in this part, right? Because of that, I'll be having 100 samples present. So what we are doing is we are taking 20 milliseconds overlap. So 10 plus 20. So we have 20 milliseconds section which is taken, and from this 20 milliseconds, 30 milliseconds, what we do is we take the peak value of the first 100 samples. So 10 milliseconds means the 100 samples, first 100 samples, and we take the absolute peaks of the last 100 samples. So we have to take these two. So, and we have to identify what is the clipping level. Now, what is the use of the clipping level? Now, clipping level helps us to identify whether that information is uh, voice or not, whether that information, whether that pitch is related to voice or not. So that is what it is trying to estimate. So we have 30 milliseconds this thing. So first 100 milliseconds part, that sorry, 100 samples, that is 10 milliseconds part is chosen. Its absolute peak value is chosen, and then the absolute peak value of the next last 100 samples, that is 10 millisecond samples, is chosen, and we try to see what is the clipping level that we can set. So once the clipping level is set, we use it for the next purpose, that is center clipper infinite peak clipper. So that is for this purpose. So here what we are doing is, once we have identified this, we pass it through the autocorrelation computation. So which gives us the information related to this aspect. So if it is 0, if either of them is 0, if it is +1, if both are equal, and it is -1 if this condition is satisfied. So based on this clipping level, I try to identify, I'll be getting the autocorrelation computation. Then we find what is the position related to this autocorrelation peak value. So whether it is 0, +1, -1. So we'll be trying to identify the position related to these. So before going here, you can see that these 30 milliseconds is also provided to this clipper part. Then it is also provided to computation of the energy, which compares this peak signal with the silent threshold. So it tries to identify whether there is any speech present or not. If not, then what has to be done. So that is what we are trying to uh, achieve here. So here we can see that compute silence threshold. So what is the level of threshold beyond which I should identify the voice? I should identify a signal as a voice. That is what we are trying to observe here. So if this energy is beyond this level, right, then it is not related to silence. So it is related to some voice which has been generated over. And when we pass this information, when we take this 30 milliseconds and combine it with the clipping level, right, we try to identify whether it falls at which position. So based on the peak value of the autocorrelation, whether +1, -1, or whether it is 0. So we try to identify that. And we compare these threshold values and try to see what are the voiced and unvoiced information over here. So this is how your clipping autocorrelation pitch detector works. So pitch detector basically tries to see what is the clipping level. And if it is beyond the clipping level, it is identified as voice. And if it is below that clipping level, it is identified as non-voice. So this is how it goes on. Because sometimes you may cough. So that is not actually your voice signal. I cannot translate it to anything. So such kind of signals also have to be identified. Sometimes you're not speaking. So even that also has to be identified. And when we are speaking, what words are put in. So those are things we need to identify. So these are the three things what we'll be identifying using that three-level center clipped signal. So this is what is happening in case of the speech processing system. This is the thing what is happening in speech processing system. Now coming down to the next part, image processing system. Now, in image processing system, DSP finds its multiple uses. Say in machine vision, you might try to detect the object, you might try to classify that object, you might try to read something present in that image. Say if you want to identify the number plate of a vehicle, so you have to identify what numbers are present in that number plate. So it is the character recognition within that image. So apart from that, again, you might go for image denoising, image dehazing. So and apart from this, even compression is also one part which is present. So how do I go ahead with image processing system? So these are the aspects what are related to image processing systems. And we see that compared to signals, right? Signal is one dimensional, image is two dimensional because it will be having two this thing that is x and y. So if I take a image, right, it is in terms of pixels. So it is divided in this form. It is divided into rows and columns. So this is one pixel, this is another pixel, this is third pixel, so on. So here we have taken a simple form. So in one dimension, that is two dimensions, the information will be present. So this is two-dimensional aspect. So one of the compression here we'll be discussing regarding the compression algorithm for the images, because when we consider the images, you can see that images can be of very large size. So you might have come across this term that image is in JPG form or JPEG form, or it is in say PNG form. So these are all different techniques of in which the images are stored. So JPEG is a compression method. It is a lossy compression method. Lossy in the sense when you compress the information, you will be losing some information. You will be losing some data from that image. So that loss of data is such that it does not hamper the overall image. For example, if you click an image, if you take an image, in that image, if noise is present, so noise is generally a high frequency content. So if you are able to remove that noise, you are again reducing some number of bits over there which are present, but at the same time you are not disturbing the overall image. You are removing that noise and you are making it much better. And sometimes some low frequency signals are also present, which have to be removed. So these are the compression techniques which are used for image processing. So JPEG, this thing is an compression technique. JPEG is an compression technique. In short, it is termed as Joint Photographic Expert Group. It is Joint Photographic Expert Group. JPEG stands for that part. So here, what has to be done? Here, what is done in this case? So here we have the original image. So original image is divided into a block of 8 by 8, a block which is of size 8 by 8. For example, if you take an image, it might be containing say 100 rows and 100 columns. 100 rows and 100 columns. So what does this 100 rows and 100 columns means? That you have in one row, you have 100 pixels associated in, when you come down to column, you have 100 pixels associated with those. So you have 100 into 100, that is those many number of pixels present in one image. So when you capture the original image. So if you want to apply JPEG to this one, right? What is the first step they do is they divide this original image, say 100 by 100. What I have taken the example. So this is divided into a block of 8 by 8. For example, that is 8 into 8, 64 pixels will be present in that sub part. The entire original image, the entire original image will be divided into subparts which are having say 64 pixels. So that is 8 by 8. 8 here, 8 here. So when I estimate, it will be a 64 pixels together. So I'll be dividing this entire image into 8 by 8 block. So each block of 8 by 8 size. So once I divide this image, right, I pass it through discrete cosine transform. So what is happening in discrete cosine transform? It is using this equation to estimate what is the coefficients. What are the coefficients? So you basically what you're doing is you're transforming it from the say we say it as xy domain to uv domain. That is from x and y domain to the frequency domain, which are related to x and y respectively. So here we can see that f of xy. or yx is associated with f of vy. In a Fourier transform, you write many times, right, in one dimension. We write it in this form. If you pass a signal f of x through Fourier transform, what you'll be getting, you'll be writing it somewhat in, so instead of this one, what we'll do is, we take continuous signal, say for example, continuous signal x of t, we pass it through a Fourier transform, and what we do, we get x of f. So this t, that is time domain, is transformed to the frequency domain. Now this is one dimensional. Now image is two dimensional. The same concept applies, but what happens is image is consisting of two parameters, x and y, because it will be like this. It is x and it is y. So when I pass it through, say for example, Fourier transform or DCT, what happens is this gets transformed to two frequency parameters, one associated with this one and the other associated with this one. Say that is rows and columns respectively, what we have. So these are the frequency aspects. So that is what is happening in this case. So this is how it appears. This is 2D discrete cosine transform, because the image is in two dimension. So this 8x8 block is taken, it is passed through DCT. Now since I have 84 blocks, what happens is if I pass it through DCT, right, I'll be getting around 64 coefficients. So I'll be getting 64 coefficients at this point, because each block is of 64 pixels. And now after this, what happens is we pass it through quantization. So what happens in quantization is these coefficients are assigned with more number of bits. They are assigned with more number of bits. And once this is done, right, it is given to the Huffman encoder. So I guess you know what is meant by Huffman encoder. So what is done in this case in simple form? If you have a very long sequence, if you have a very long sequence of information, say the coefficients, what you do is you assign a smaller code to this. You assign a smaller code to this. Smaller code to this. By this, what you're doing is very larger. This thing is represented with very small number of bits. So that is what you're trying to do here. So this is how compression can be achieved over here. So if the coefficient and you pass it through the quantizer, you'll be getting coefficients with different sizes associated with them. That is different number of bits associated with them. See, the larger number of bits will be encoded in with the smaller code. The larger bits will be encoded with the smaller code. So this is what is happening with respect to Huffman. So this is very simple, this thing what I am telling. So you can just have a look at how Huffman encoding actually works around. So this will give me the compressed information. So this is your JPEG image what you'll be getting. So original image will be converted into compressed image. Now when we come down to this part, right, that is decoding, we have to do the other stuff. So I have the compressed image. I have the compressed image. So since I had done encoding here, I should decode it back. So based on the code what is present, you try to get back the what are the original bits. And since you had done before this, you had done quantization. So after this Huffman encoding, you should go ahead with dequantization. Dequantization, that is remove the extra bits what you had put in the quantizer block using this dequantization table. And before this, you had done DCT, right? So here what we should do, we should do inverse DCT. We should do inverse DCT. So now here what happens? So here we had seen. So here we perform, for example, I have to, which is inverse Fourier transform. So when I do this, I should be getting back this information. So I'll be performing this IDCT and I'll be getting the recovered image. Now in this process, you might be losing some of the information, but you try to see that not much of the information is lost, which actually hampers the overall image quality or other stuff. Only say signals with very high frequency which are related to noise, they are tried to eliminate. So such kind of things can be put forth. So this is the JPEG decoder. So the decoding equation will be opposite of this. This part will be remaining same. This will come around along with these two parameters. That is the coefficients. So here we can see that this parameter, the other things remain same. So this is how image compression works around in using the DSP. So these are the applications which are few applications which are related to DSP or DSP devices. So any query from your end? So next we have interfacing memory and parallel I/O peripherals to the programmable DSPs. Now what happens is previously we had seen that it is better to go ahead with on-chip memory as compared to memory which is present in the external. But in some cases this is not feasible because we require extra memory also, or we require some extra interfacing devices. So such cases we have to go for interfacing of memory in the external form and also the other devices which are required. Say I want to have a keypad attached to the DSP processor and it is not present in a DSP, then what I have to do is I have to externally interface it. So how do I go ahead with these kind of interfaces? So first one, what we have the memory space organization. So whenever we have to start off with programming or any other stuff, so we should know how the memory is organized because we have to go and access some information over there. So in order to do that, we should understand how it is connected, what are the signals which are required, what are the interfacing aspects which are required if I have to go and access it or store something or do some memory related operations. So I should check out all these things. So here we are just taking one DSP processor which is termed as TMS 320 C54 and any series would be present over here XX. So based on the series and the other devices, slight differences may be there, but these are just a few common things which are present over here. So what we have is the first basic memory, which can be either internal and external, which can be around 192K. That is 192 K bits of this thing. Each which is of 16-bit word. So one location will be storing 16-bit word. So if you have a memory, right? If you have a memory, one location will be storing 16 bits of information. So that is 16 bits of words is present. Now here, what we have is this 192 is divided into three parts. That is each of 64K words. So that is one for program memory, one for data memory, and one for the IO space. So total three, this thing it is divided. Now, the program and data memory can comprise of both on-chip and off-chip memories because in some cases, if I require external memory, right, then I have to go for that external memory and access it. So I can have this combination. That is, I can have both internal also, both external also. But using on-chip actually increases the speed. But everything I cannot do it over here. Then in that cases, I have to go for off-chip memories. So if I just see this 192K 16-bit words is divided into 64K words each, one for program memory, one for one for data memory, and one for the IO space. So when I add these three, I'll be getting 192K. So that is each word is of 16 bits. So that is what it specifies. Then depending on these devices, right, there can be a different on-chip memories which can be RAM, DRAM, SRAM, or any combination which can be present over there. And when we are dealing with memory, right, we have to deal with some registers so that we can access that memory. We can try to understand what has to be. Suppose I want to go and access ROM. So how do I access ROM? I have to go and see the status or check the put the status of the registers so that I'll be going and accessing that part. So here we have three CPU registers associated with that. This is micro, say processor. This is a micro computer. So this is one register we can utilize for setting this. Then we have something called as OVLY and DROM. So based on these three CPU registers, we can check out the memory of a device which is mapped to the memory space. So this is how we can go around. So that is what he has specified in this blocks. So here we can see that if MP/MP bar, so that if this pin or this interface is 1, so the entire stuff will be operating in microprocessor mode. So and if this is 0, it will be operating in microcomputer mode. Then you have the addresses which are present over here, which is 64K. So 0 to this one 64K. You can see that from this point to this point, you have interrupts which can be external. then the external parameters which are present over here, then you can have on chip and the reserved parameters. So here, if it is reserved, this thing OVLY is 1, and if it is 0, it is external. And similarly, you have DRAM on chip when this one is 1, and if it is 0, it is external. So these are the memory spaces again, which the 64 is again divided into this space. So in this case, again, it is divided in different forms. So you can just observe from these parts. So this is related to the program, and this is related to the data. So this is again the 64K word. This thing is again divided into these parts. So this is just an example what we are specifying over here, which is for 5416. So again, different this thing, if you go, slight differences might be observed. So here, now here he gives an example of, say here we had what? We had total of 192K words of memory. Now in some cases, what we can do is we can extend this memory up to 8192K words, 8192,000 words. So if you have to extend, so this is what they have presented. So this is actually related to 8192 extension. That is memory is around, if I specify it as 8K words, it is 8K, sorry, not 8K, 8 megawatt, 8 megawatts, because it is 8192K words. So 192, this thing is extended up to this point. So that is what is shown in this diagram, extended memory. So you can extend this memory up to this point. So this is related to the memory. Then coming down to the other part, that is external bus interfacing. So we require the external bus interfacing because we have to go and access the data. We have to go and access some other information from there. So in order to perform that, we should have the bus interfacing available. The interfaced with the peripherals using these things, that is address bus, data bus, and the control signals associated with them. So if I have to interface this is how I can go ahead. So we'll be stopping here.